Hey everybody, this next video lesson is going to discuss something called electrolysis in electrolytic cells. We're also going to touch on the stoichiometry involved and how to calculate some masses from electrolysis in electrolytic cells. First of all, what is electrolysis and what is an electrolytic cell? Well, voltaic cells by definition always have a positive cell potential, which means they always spontaneously go from reactants to products. But an electrolytic cell is a non-spontaneous, but it's essentially forcing a non-spontaneous redox reaction to go using an outside power supply. What's interesting to note is that the process of photosynthesis is non-spontaneous, but a plant harnesses the energy from the sun in order to force this non-spontaneous reaction to go spontaneously in the forward direction. It is essentially an electrolytic cell. This process is most often used when it comes to taking metals and plating them onto other metals. Have you ever heard of the concept of zinc plating or chrome plating or copper plating? Oftentimes, this requires taking a piece of metal and dipping it into a solution that contains the ion and forcing the ions to plate themselves or attach themselves onto the other foreign metal object in the process known as electrolysis. Usually this happens at incredibly high acidic conditions or incredibly low pHs, and it uses a high voltage power source in order to make this happen. Now, I've tried to do this in lab, but there's lots of variables that go into this. But I have successfully plated zinc onto a copper penny. It wasn't pretty, but I did it using a high voltage power supply. You're looking at an electrolytic cell, and the goal of this electrolytic cell is to take a piece of steel and plate some nickel ions onto it so it has a nice nickel shine to it. Now, the way this works is you have an electrode, the anode in this case being pure nickel, and you dip it in a solution of nickel ions. Now, you hook up the power supply so that it basically draws electricity out of the anode and towards the cathode. Now, this reaction won't happen spontaneously without this voltage source here in place. It will not go. But when you turn it on, it basically forces the electrons to go from the nickel anode across the wire and down into the steel object. Now, nickel solid dissolves into the nickel solution. So the concentration of this goes up slightly, but as the concentration goes up, then those nickel ions plate themselves onto the steel object. So over the course of a number of seconds or even a couple of minutes, you get more and more atoms of nickel ions plating as solid nickel onto the other object dipped into the liquid. It's almost like nickel throws the electrons to itself on the other side. Imagine playing catch with yourself. Nickel throws the electrons up, migrates across, catches them on the other side, and in the process plates itself onto the steel object. Now, that sounds ridiculous, but it's possible and does work. So at the anode, solid nickel is becoming nickel ions, but at the cathode, an equal amount of nickel ions are becoming solid nickel. And the object in the middle stays the solid, but it then gets plated with a layer of nickel. And the longer you let this run, the thicker the nickel plating occurs. I'm going to take you through a new type of stoichiometry that we're going to talk about that deals with electrolytic cells. We'll call it electrolysis stoichiometry. I'll show you a couple of examples of different problems that deal with this flow chart over here on the right-hand side of the page. Now, I snagged this once again from our textbook, but I didn't really like it, so I edited the top box. I'm going to call that one time. So let's say that you run a high voltage power supply for like 60 seconds, and you want to know at the end how many grams of substance will you have plated after that time. Well, here are the steps that it would take. First of all, you have your starting number, time, in seconds. Now, how do you get from time to quantity of charge? Well, as we talked about, that requires you to know the amperage of the power supply. Now, amps are coulombs per second. It's basically how many coulombs of charge that will be discharged from the power supply per second. In other words, it's a rate of electrical charge transferred. And so, if you know the amperage, you know the coulombs transferred per second. Now, from coulombs of charge, you can then convert to electrons, specifically moles of those electrons. And in order to do that, you use Faraday's constant. So to go from quantity of charge to moles of electrons, you use 96,485 coulombs per mole. Now from there, it looks like traditional stoichiometry. You take moles of electrons and convert to moles of substance that you're trying to oxidize or reduce. That is a simple mole-to-mole ratio. But instead of moles of substance A and moles of substance B, you're going from moles of electrons to moles of substance. And then finally, you use a quick molar mass to convert from moles of substance to grams of substance. And those are the steps that you would take in order to do electrolysis stoichiometry. Now let's just say that you know you have 500 grams of substance plated and you want to know how much time it took to plate that 500 grams. Well, you could work this process in reverse. You could start at the bottom and go grams to moles, and then convert moles to moles, and then use Faraday's constant, and then, once again, the amperage to calculate the amount of time it took to plate that amount of grams of substance. The key here, once again, is making sure that you know how many moles of electrons get transferred in the redox reaction. Total moles of electrons is important in order to figure out this process. So make sure that you know how many moles of electrons, and you can figure that out once again by using the half reactions and combining them to calculate the number of moles of electrons transferred. Now I'm going to show you a couple of different practice problems that deal with electrolysis stoichiometry. Now if you downloaded the blank template of notes, then this is actually the second of those 3 practice problems that I showed you in the template. I actually moved the first one to the end because it is the most difficult, in my opinion, of the 3. So skip the first one and go on to the second one that deals with gold. It says gold is plated from a solution of chloric acid. Well, I don't really know if I pronounced that right, but it's HAuCl4. It deposits on the cathode. Calculate the time it takes to deposit 0.65 grams of gold passing the current of 0.1 amps if Faraday's constant is 1 mole for every 96,485 coulombs. If you're following along in your notes using the flow chart that I showed on the last page, we're actually starting at the bottom because I have the grams and I'm trying to figure out the amount of time that it takes. So I begin 0.65 grams over 1. And I use the molar mass to figure out how many moles of gold, because that's what I'm trying to figure out. And I have the molar mass up there in the problem, 197 grams per mole. Next, I figure out the moles of electrons transferred, but it's not obvious to me at this time. Basically, gold is going to be plated and it has 0 oxidation state. So I got to figure out what's the oxidation number of the gold in this substance right here. Well, each chlorine should be a -1 charge. So if that's the case, then 4 of those is an overall -4. And hydrogen is always a +1 charge. Overall, because of the rules of assigning oxidation numbers, these all have to add up to equal 0 because the charge of this molecule has none charge on it. So if hydrogen's a +1 and the 4 chlorines are all -1, then gold must be a +3 charge. So if it goes from a +3 to a 0, then it must transfer 3 moles of electrons. So now I've calculated the number of moles of electrons. Next, I use Faraday's constant, and I take 96,485 coulombs over 1 mole of electrons. And then finally, I take the amperage. Now, the amperage is in coulombs per second, but I want the coulombs on the bottom, so I put 0.10 coulombs on the bottom and 1 second on top. Now, when I multiply all this information together, I have 9,551 seconds. Now, it doesn't match any of my options here, but let's take a look and see if we can convert those seconds into hours. Now, there's 3,600 seconds in 1 hour, 60 seconds in a minute, 60 minutes in an hour, so 60 times 60 is 3,600. So if I take this number and divide by 3,600, I get 2.65 hours. Well, hey, look at that, letter B, 2.7 hours. So by running this amperage for 2.7 hours, I will plate 0.65 grams of gold. Notice the amperage isn't very high. 0.1 amps, it's not very much. But it's a slow process, but I will plate 0.65 grams of gold. Here's an example of one where we'll start with time, and we'll figure out how many moles of the Mn in MnO4 is reduced to Mn3+. Now I've got an amperage of 7.32. Now remember, amps are coulombs per second, and that's passed through a solution for 15 minutes. What are the number of moles of the Mn3+ produced in this process? And once again, I gave you Faraday's constant there. Now this time, I'm going to start with the time. And the time is 15 minutes. So I need to convert that to seconds, because then I need to use the amps to convert to coulombs. So if I take 60 seconds over 1 minute, that will convert it to seconds. Next, I use the amperage in coulombs per second. I put 7.32 on top, 1 second on the bottom, and then I'm going to use Faraday's constant to calculate how many moles of electrons on top for every 96.45 coulombs on the bottom. Now we're at that point again where I need to figure out what the oxidation state change is of the manganese. You see, it started out as this substance and ended up as a 3+. And I need to figure out how many moles of electrons got transferred. So once again, I need to do some investigative work here. Now each oxygen is a -2 charge oxidation state, and there are 4 of those. So there's a total of -8 for the oxygen. Now whatever manganese is has to add with that -8 to have an overall charge of -2, because again, the rules of oxidation numbers say that the oxidation numbers of the elements in a molecule have to add up to equal the charge of the overall polyatomic ion. So if all the oxygens give us a -8, then this manganese must have started out as a +6, and that's the number that it started at, and it ended as a +3. So you can see that 3 moles of electrons were transferred to reduce it from +6 to +3. So now I go down here once again at this last step, and I put 3 moles of electrons on the bottom, and I put 1 mole of manganese 3+ on top. And then I've got all the numbers I need. So then I plug it into the calculator, and I punch these through, and I get 0.0228 moles, which matches letter D. Now we're going to tackle this last one, which, as I mentioned, I moved from the first practice problem to the last practice problem, if you're looking at the blank template of notes that I provided for you at the beginning of this chapter. So this time we have an unknown metal. We're trying to figure out what the identity of that metal is, and the only way we can do that is to see if we can figure out the molar mass of that metal, and then compare it to the known molar masses of the periodic table. So what makes this problem difficult is I have time and grams, and that could be numbers that I start the problem with. I'm going to save the number of grams for later, and I'm going to use it as part of the molar mass. So my plan is to take the time and the amperage and figure out how many moles of M will be plated, and then take that mass and divide by the number of moles to figure out the molar mass. So I begin with the time, 52.8 seconds, and I use the amperage, which once again, amps are coulombs per second, so I put 2.0 coulombs on top and 1 second on the bottom. I multiply that by Faraday's constant, which has 1 mole of electrons on top and 96.45 coulombs on the bottom. And then finally, I figure out how many moles of electrons of that M. Now it started out as part of a solution of M nitrate. Well, each nitrate's a -1 charge ion, so M must be a +3 charge ion. And it went from +3 to solid metallic M, which is 0, so that must once again be 3 moles of electrons transferred. Now I realize that all 3 of my practice problems that I've shown you thus far have had 3 moles of electrons transferred, but just understand that that was mere coincidence, and you're likely to see any other number in addition to 3 moles of electrons in any future problems. So just pay attention. It's not always going to be 3 moles of electrons. Anyway, I've got all my numbers, and I put it in my calculator, and I stop here and I calculate moles of M. It's 3.65 times 10 to the -4 moles of M. Now that moles of M is going to go into the bottom of my molar mass, and I'm going to take the grams of metal M and put it in the top of my molar mass, and then I divide those 2 numbers, and I get 197.08 grams per mole. And I look on my periodic table, and I find the element that's closest to it, and the gold is 196.97. Well, that's pretty close. The one next to it is mercury at 200, that's too high, and the one next to that is platinum, which is 195, which is too low. So I can be pretty confident that the unknown metal in this case is gold, or AU. Well, that takes care of this video lesson. Thanks for watching.